If you guys have any questions, feel free to raise your hand and ask questions, or there's a Slido link that is on the meetup. If you want to ask an anonymous question, feel free to just submit your question there on meetup. And please include, there's food over here, if you haven't already.
Is it recording?
Yeah, it's live. All right, thank you for joining us. This is the first meeting we've had in a while here with, at Chapman University. We're very excited for Emil's presentation, Stop Horsing Around, Ship the Query. I see a few new faces here, and I know there are several people online. So just to kind of give you a little background about Southern California, our users group, we're a nonprofit. We try and encourage knowledge sharing and networking and just, fun conversations with data science practitioners, researchers, academics in the Orange County areas, LA and Orange County. We have partnerships with UCI and Chapman University. We do workshops at UCI. We have advanced regression workshops, some Git workshops to get you up to speed on how to use Git and version control. And we've had, I'll talk about advanced regression workshops. We've had hackathons in the past. So yeah, please check us out. Meetup is definitely the place where you want to, keep in touch with us. That's where we post most of our events. We want to thank our sponsors, especially Chapman's Fowler School of Engineering. If you are looking around for schools and you're interested in pursuing a graduate program for data science, they have the MS in Electrical Engineering and Computer Science program. There's a few different technical tracks, data science, computing systems, electrical systems, and actually one of our SoCal RUG coordinators, she used to be a professor here at the school. They teach a lot of natural language processing and deep learning methods and really neat stuff. So if you're interested, please check out this program. We have a bunch of social media contacts here, but for the most part, all of our events are posted on Meetup. That would be the place to go. And yeah, that's about it. Without further ado, we want to present Emil Hvitfeldt with his Stop Horsing Around, Ship the Query. Emil is a software engineer at Posit PBC, the company formerly known as RStudio. He's a proud co-author of Supervised Machine Learning for Text Analysis with R with Julia Silgi. His interests include developing tools for natural language processing, machine learning using tidymodels, education, the use of colors in data visualizations, and a lot more. So thank you. And for those of you online, if you go to the Meetup event page, there is a Slido link that is in the description of this event. If you have any questions, we disabled the YouTube live chat, but please go in there and you can post your questions on Slido. All right, thank you.
All right, thank you for the introduction. All right, I'm excited to talk about Orbital today. It's a thing I've been working on for the last couple of years. Technically working on it for half a decade, but it became a thing a couple of years ago. All right, so we start off making just a simple classification model, or machine learning model right here. I'm using tidymodels, and I'm using the Penguins data set, doing some rudimentary feature engineering, pre-processing, and then fitting a quite shallow decision tree. The details here isn't really that important. The important thing is that we have a fitted model that we want to do something with. But we have a model, and the next question is often, what do we want to do now? So depending on what we want to do, it is prediction. We're trying to build some kind of decision-making tool that helps us further something. So I'll mostly be focusing on prediction for the remainder of this talk, but there's many other things you could do with like a model. There's a lot of inference and other things which can really happen. So normally in tidymodels, we call the predict function on our testing data set, and we get back a prediction as a tipple. And that is all well and good, but depending on what you do, you might have a lot of data, you might have data somewhere else. So this is where like the ML ops world comes in. Like, can we do prediction somewhere that isn't on my computer? One way of doing something like this is the tidypredict package. So Edgar wrote this a handful of years ago, and it basically allows us to run predictions in a database. So it passes a fitted model, extract what it needs, and then generate an R formula that we then can translate into SQL. And it offers a wide variety of supported different types of models that are translatable. So these are all things where we can pull out some type of math that, when evaluated, does the same thing as the predictions. So some things we can't do. So anything like nearest neighbor methods don't really work because the math itself, or technically it would work, but the math would be huge. So any linear regression type thing worked well. Trees work because it's basically just a series of if-else statements. And there's some other type of models too, but these are like some of the supported models in tidypredict. But the reason why we're kind of doing this talk and why I'm talking about Orbital later is that tidypredict is just limited enough that it isn't entirely useful. Because you can't do pre-processing and post-processing because we're limited to one iteration, the one R formula that we're evaluating. It gives entirely two redundant calculations, and then because of the limitation of one iteration. So if we're doing centering and scaling, which is like part of the pre-processing, and a variable is being used many times, such as in a tree-based model, we have to do the centering and scaling each time it's used in the tree, which can be like very inefficient. And also it becomes really hard to do probabilities because we have one iteration, we can get one thing out. So we can get one type of class probability out. But if we want to have a multi-class classification, we need to rerun everything for one person, then one iteration. So, and kind of giving a very short example of how tidypredict works on a very superficial level. So here we have the tree I built, which is very shallow. It's depth 2. So we have a total of 3 splits. So it's a really small tree. And this is how it does it. So we start the root. If the build length is less than minus 0.2, remember these are centered and scaled, so this is not the actual length of it. So if it's less than this, then we asked, is the set male variable more or less than this, and depending on what we did predictions. So there's just 4 end nodes here in this tree. We can rewrite this as a series of if-else statements. This would return the same thing as our tree for a single prediction. And we can then rewrite this as a case-when statement from dplyr, and then doing the same thing. Now we have it as a one expression. Technically, the if-else before are one statements too, but this one is a vectorized version. So we can apply this in a dplyr pipeline, and we would get the same predictions as if we were having doing predictions normally. So I'm pulling up a little bit a more our workflow that we used before, because I want to talk about how a workflow happens. This one has a lot of our pre-processing steps, feature engineering steps, and our fitted models. So in tidymodels, we believe that you should always do all your feature engineering inside a workflow because it needs to be coupled with the model fit itself to avoid any type of like overfitting, data leakage, all of that. So we specify all of it here. And then when the model is fit, we calculate all the sufficient information that is then reapplied later. But it happens in the order as you see it. So the first thing that happens is that we deal with unknowns, then we impute with a median, then we create dummy variables, center and stale, and so on. Here I also have the step N CV and step TOR. So the first one removes near zero variance predictors. So a zero variance predictor is one that has the same value for all the observation in the training data set. That variable doesn't have any information at all. It should be removed before putting into a model. And I'm also removing some TOR-related features. And then it isn't super important what we're doing, but it happens in this order. So we should rewrite that, and it's a little small because that is just what happens. But this is basically all the things that happen underneath the hood when we do predictions. The species and island has a if else, is this NA, then we give it an unknown, otherwise not. So we're imputing, centering and staling, and so on. Like here, like these three ones is essentially what happens. It isn't what actually happens, because it's coded a little bit differently. But this is equivalent computation as what tidymodels would do. So these lines correspond to what happens when we do step unknown. These ones are equivalent to impute median, step dummy, step stale, step center. At the very end here, we have what the prediction will be. And this is the case when statement we saw from earlier, just not formatted just as nicely. So if you ran all these lines in a deploy pipeline, you would get the predictions that are equivalent to the model predictions that we saw earlier. But what we notice here is only some of the variables are being used. So we are only using the dummy variable set male and bill length and the species chin strap. So we're using 3 different variables in our final decision tree. So we can actually highlight those earlier here in our centering step. We're technically only using these 3, so we don't have to calculate these other 5 because they're not being used later on. And we then repeat that, looking at these are all the ones used in the staling step. And then some of them aren't being used. We don't have to calculate them. And we can really technically throw up and realize, since we're not using all the variables later on, we don't need to calculate them further, which means that we can take this series of equations and reduce them down to this series of equations. So by calculating sufficiency moving backwards in time, we are able to only calculate what's needed. So this becomes, yes?
Stupid question.
Yeah.
Why are they calculated to begin with?
Why are it? So the question from the audience is, why are they calculated to begin with? So when we do fit the model, it does it forward to back. So it doesn't know. So when we're doing the centering and staling, it doesn't know that the tree doesn't fit them. Technically, once you fit the model, you should go back in and update the preprocessor to don't do it. We haven't implemented that yet because that's really hard. And some things becomes weird because sometimes you have things where it does something as a proportion, and if you remove it, you have to be a little bit careful. But technically, that would be a thing to do. We haven't because there's over 100 recipe steps, and I would be the one to do it. But essentially, in this way of doing it, we can reduce something, sometimes a lot. This is a toy example, it's penguins. But you should imagine that you had 100 predictors and you're using a lasso regression, and then suddenly you're removing 90% of them, and thus also removing like 90+% of everything before, really increasing the speed. And this is where Orbital come in. So we have our fitted workflow, and we applied the Orbital function to it, and that one does what I just shown. It passes the workflow that includes the model and the preprocessor and generates all the sufficient calculations in a way that when they're being run, generates what the predictions would have to be. And so this is not the sufficient way. Here is how you would have to have done it if we had done it in the tidy predict way. So here we have one statement where I have folded all the steps backwards into each other. And we're getting all the, not only are we saying like, is NA set multiple times, we're actually saying like, ask numerid of if else of something divided by something minus something. So this thing is being calculated multiple times, and only twice here, but I've seen examples where we're reducing, by doing it the bad way, we produce like hundreds of times more code to be calculated because we're doing it inefficiently. So not only are we doing things sufficiently by only calculating what's needed, we're also only calculating it as many times as we have to calculate it. So now that we have our orbital model, which is just a small model, we can do a couple of things with it. So let's start with prediction. So here I'm doing predict on the orbital object, not the workflow, and we are getting the exact same predictions. So technically, the first benefit we can get from using Orbital is you can save this orbital object to disk, load up a new R process, load Orbital, and run predictions. You don't need to load up tidymodels or the engine or something else. We have a much smaller dependencies because this thing only need like dplyr and rlang to do predictions. So we can drastically reduce a data container because we only need the orbital object, which has a JSON format, and then a couple of quite low dependencies. So that's like one benefit if you want to do predictions. Yes, question from the audience.
So in the example where you were showing the prediction
equals
3985, basically you would need to know the answer for every combination of inputs. Like, is there some kind of index that's built into Orbital, or is that the math that you're abstracting?
So, yes, so all the orbital methods that I have here, I have, at least on they're all handwritten. So like we extract all the things we need and then generate as code the things, if that made sense. Yeah. So here we have like, so we do predictions, and you will see here that they're doing the same thing as the workflow up to precision. So like we always have that machine precision sometimes. So like it's sometimes off in like the order of 10 to the minus 15. But it's basically the same predictions we have as with our normal predictions. So we can predict with a tibble. It's like, oh, here's a tibble, we predict with it and it works. But we can also predict in a SQL database right away. So here I'm putting up ephemeral SQLite server. I'm adding the Penguins dataset as a table in this server, and I can predict with this orbital object directly on the database. So these calculations happen inside this database that in the slides are like locally, but if you can connect to any database outside, it will do, and calculations happen in the database. And it works with basically anything. So you can also put it directly in a Spark cluster. It works with .db and technically Arrow. So if you can data connection to a database and you have the data set in there, you can run the predictions on the database itself instead of on your pulling the data into your system. Yeah. And in a similar vein to all of that, we can do this thing called code generation. Because the reason why all of this works is because we're using a DB plier underneath the hood. So here I'm having a connection to my SQLite database because all SQL flavors are different. So you can't translate to SQL as a command by itself because each flavor uses different syntax in some cases. But basically, I can take my orbital object, pass in my connection, and generate the SQL that when run in this type of SQL database, it then produces the same types of predictions as you would have if you have run them in person. So this is where it becomes a little bit exciting, because this means that the question really is, why should I care? I showed a thing, and but then is it useful? There's a couple of reasons why this is bad, and this because doesn't support everything. So I said it doesn't handle nearest neighbors methods and other weird stuff. So it has to basically have math that we can write down that can be run in a line by line mutate type way. And it doesn't do input checking. So as you saw, the code I showed before was what was being run. So if you're predicting something new and something turns into a string instead of it being a number, it's going to try to add the string. And if you're lucky, you did an error. If you're unlucky, you just did an NA out of the end. So there's no checking, which also it's part of the speed. It's it's fast, but it's up to you to make sure that it's actually the data is clean enough for it to work. But we have some big pros in this. So as I showed before, you can create a Docker container with a very limited number of R dependencies that does predictions. They are not always faster if you do it that way, because it's just a series of statements and they're going to be more inefficient than matrix multiplication, which is underlying a lot of this, a C code that runs all of this. With new prediction databases, which I will show as a demo at the end, we can generate this code, and sometimes we did it at really, really fast speeds. And I have a slide with some examples about that later as well. Yeah, and then we can generate SQL, put it in a database, basically doing MLOps without any of the MLOps platforms. It is, and the reason why we want to put stuff in a database to run predictions is I think it's simpler because you don't need to put anything up. It's basically just, here's a SQL file, and IT loves SQL and doesn't like R in general. And it's way easier just saying, hey, can you put this SQL file in this thing? And most of the time it works. And you also get this weird setting order effect that since it's SQL, you didn't hand it to someone that isn't technical in the R modeling setting. So you allow other people to do predictions because they don't need to learn R, Python, modeling. They just have to run this script. And we have also seen a lot of speed at some of the users. So we have a customer who had a script that would take 2 hours to run predictions that now takes 24 seconds. And I will show this later. You can do millions of predictions per second, as in observations. And I talked to multiple users that run this with hundreds of millions of observations every day. So it's very, and all of this happens because it happens in the database, and people that make databases really care about making that fast and efficient. So it's not really what I'm doing. It's just using a common format like SQL is amazing because that makes sense. So
Questions now or at the end?
this question will be answered later. So there's a couple of, most of this is basically what I said at release. But we had a couple of new things happen since then. So one of them is now we also have classification support. In the beginning, we only had regression. We also have regression. We have classification now. And that was partly because it was hard to add classification, but it adds a little more. So here I'm rewriting the model. Now we're doing, now we have a classification model where we're predicting species. And running Orbital on this one now gives us our series of iterations that when run does the class prediction. So here, these lines up here is all the pre-processing that we've seen before. But to make classification happen, we here need the model to produce 4 things instead of 1. So essentially, most classification models work by each of the classes data probability, and you look at which one is highest. We don't technically need to normalize them because it's fine, but the normalization factor is the same. So here, it creates 3 columns, one for each type of species that calculates its quote-unquote probabilities. And then the hard prediction is then a case when of is this one larger than all the other ones? And then if not, it's like basically you can write an if-else case when state that using the class probabilities gives us the hard prediction. But we can also do probabilities. So everything is the same, but now it also calculates the normalization factor that when a like kind of raw probabilities actually create probabilities that now sum to 1. And then these calculations is the same as what you would get with like the normal prediction method. One thing that's worth noting when we do classification with Orbital is that the Orbital object needs to have specified what type of outcome we want, because it's generating everything we need. So you can't create the object with type class and then ask for probabilities later, because it doesn't know how to deal with that, because it loses the original object to keep itself light. But it also shouldn't really be an issue for you to do it. It's just a note. Another thing is we have augment support. So augment is technically a Broom function that I think is very useful in a modeling setting. So what it essentially does is it takes a predict and bind the original data set to it, because that a lot of times is really useful. So here we're doing is because now we have the predicted class and the original class. So now we can do an augment into a accuracy or ROC or whatever. So with that, this is just a useful thing. And now we have support for that in Orbital. And then it also works in databases. So this is totally a useful thing. And I'm pretty sure also works in Spark, because I remember doing a lot of work to make that happen. We also have full Python support. So a separate package, we have a Python support. So similarly, the Python package that does it does like most of the transformers you would expect. You can't see it, but if you do Python Orbital, maybe put a Posit in there, you will see it. Sandra Sorry that I'm forgetting your exact name. But basically it was how you would expect here with generating a pipeline, applying Orbital on it, generates the SQL, and it works the exact same way. You just need to do it in Python.
Is there a limitation to the SQL dialects? Like, is there, like, I'm assuming you don't support like random legacy SQL stuff.
So the question is if there's a limitation on the SQL dialects. So on the R side, if there's a binding in the dbplyr, dpi verse, so essentially when you create like the connection, it will, there's this like lookup table of this R function is translated this like SQL syntax. So whatever that support it supports, you can technically also extend it. So if you have a esoteric database, you just need to write the spec in of this is the translations. And it's actually really easy because it is all the arithmetic, large, exponents, if else is NA. Like it's actually a very small set of operations that we're actually doing. And similarly in Python, I think it's using like SQL alchemy to do it. So, and that should also, if you have something weird, it should be able to do it. Yeah. In the developmental version of the R package, we also have Taylor support. So Taylor is our newly released package that handles post-processing in a workflow. And we have support for almost all of them except calibration. So if you have a Taylor added to a workflow, Orbital should be able to understand that and include all of those transformations as well. Another thing I'm working on as we are speaking is this thing I'm calling tree splitting. And before I move on with this, I'm going to ask the question from Slido, because it's asking if there's any pitfalls when writing SQL code for something like a tree, because like are there sometimes limits to length of valid SQL strings? So yes, some SQL databases says SQL expressions can only be so long. And only it's sad, but it might be 100,000 characters or something like that. But some of them complain saying, hey, this is too long for me. And there's two ways of dealing with that. One of them is fitting the model slightly differently. So if you remember, as an example, the HG boosted tree, and boosted trees just in general, is a series of trees that we add together. Boosted trees, when we do a hyperparameter tuning to find the best combination of hyperparameters, have a very big plateau of optimal values. There's not just one singular combination. So what you can do to make the resulting SQL smaller is to fit a tree with a higher learning rate and fewer trees and fewer smaller trees. So basically, you do your grid, and then you find all the value, like all the good models, and then you pick the ones where it has small and fewer trees. So that by itself, I did some fun examples, and I can get like a 10x speed sometimes just from that because the SQL is that much smaller. Another thing, if the SQL is small enough to fit, but it's still running a little bit slow, is this idea of tree splitting. So here I have a small tree. It's a boosted tree, so we are adding a bunch of trees together here in this regression case. So it's just one statement that is being run in our database. What we can do is we can split it up into multiple trees, run them calculate them one by one, and then adding them together at the end. They should be equivalent, but this one has 4 statements and the other one had 1 statement. This one can't be recognized by our SQL databases to be, hey, I can calculate all of these at the same time. So it can calculate, depending on how many TORs it has it up, it calculates these side by side. So then you can see like a x-fold speed up based on the number of parallel calculations to do, because the trees here are independent of each other. So for boosted trees, when this like rolls out, you might be able to see a lot of speed increases as well. Yes, so I think that's, so now we have a little bit of demo showing that it actually works. So here I'm in Posit Workbench. I could set it up on my own computer, but I don't know how. So this is like a thing we use. So I'm just spinning up a RStudio Pro session that is already configured to connect to a Snowflake session, and someone else is like, and this IT set this up for you. So like now it's already set up. So it means that now when we're in our studio here, the first thing I do is I connect to our Snowflake, and because all the permissions is up correctly, I now have a connection to our Snowflake setting, and I'll do modeling like I normally do. I load all my packages, and here I am. So here we take, like, if I run here with our connection, I'm pulling out the loan data table that has like a bunch of data in it. It's technically like 2.2 million observations. We're doing some formatting to make things happen the right way. And then I'm taking a 5,000 observation sample from the year 2026. And then 2016. And I'm doing some other small things to it. I'm removing some variables, adding some variables. Like, that's not a big thing. But I have collected this data. So now this data is no longer in the database. It is now present in my local R session. And it has a little bit less than 5,000 because we are removing things with missing values. So now that we have that, I'm specifying a model. It is just a linear regression. Linear regression works really, really well with Orbital because it is almost the simplest possible model configuration. So it runs really fast as well. And we are doing some pre-processing. All of this isn't really that important. We just have a workflow here that's specified. And I'm training this workflow on this 5,000 observations. You probably want to fit it on more than 5,000, but this is in interest of speed. It runs basically instantaneously. And I can predict on it here locally. So now but then this is not what we want to do. We want to predict with it in the database that we are connected to. So I'm running Orbital on it, and we're getting the Orbital object. We can technically, if we use the Orbital up, obj, if you use the print method directly, you can actually see the whole, everything that happens. Don't do it on bit models because like you can easily get 100,000 character long model. If you're doing anything with multiple trees, it can really blow up. Yeah, so basically we have the Orbital objects, and now we can generate our SQL. And then it's fairly small because we're intentionally doing it small so it runs fast. So, and now we can basically just run the predictions in the database. So here we have our Orbital object. So actually, we didn't need to generate the SQL just to see what it looks like, but we can run the predictions directly in the database. So here I'm taking my Orbital object, our lending club data, which is a table in our SQL, or in our like Snowflake database. So this isn't on disk. It's just like in there somewhere, and it just pulls this out enough to print it. So I will put it directly on it and saving it to this like temporary name. So we have something. So we run that. It's 2.2 million observations, and it runs in around 2 seconds on this database configuration. And we can then query the observations. Here we're doing some filtering on the NAs because I think something went wrong and we're not handling NAs directly. So if we actually look at the predictions directly, they're all NA, but there technically are some non-NA, a bunch of non-NA as well. But yeah, we basically predicted in a database and saving the results as a table in the database for like 2.2 million in less than 2 seconds. And you then technically, with the SQL up here, because it's generated, you could save that as a CTE that then like just is put into your SQL database system and have it run on like a daily setting or whatever. So like you don't have to do it here as locally. You can actually just upload it as a thing that runs on a schedule. And now we have predictions without having to spin up an R session every time. And if we go back to the thing, we have there's a bunch of links to like things Orbital done. Some of my great teammates that have showed how we can do this in more detail than what I'm showing right now. But so we have examples of how to deploy both scikit and tidymodels on Snowflake and Databricks in all the combinations, showing how we can set up a CTE in different ones. And yeah, basically it allows us to do, I think, a lot with like a good amount more with a good amount less. We have one question left is, you talked about code needed to add new SQL engine. What is the total effort to add a new orbital algorithm, e.g. causal forest? So that part is a lot more. So adding the SQL engine, I feel like that easy because you only have to do like 5 different things. I think I'll just show because it's tidymodels, tidypredict. I'll show what code was needed to do make Ranger predictions happen. Ranger. So this is all the code that was written to pull, most of the code that was written to pull out everything from the Ranger stuff. There's some couple of different things. It's a lot. Like, I won't lie, it can be very hard because basically you need to parse the structure itself and generate sort of trees. Admittedly, once you have one tree going, you kind of have a lot of them, but they're all, the objects themselves have to be parsed correctly. So most of the time it's just a bunch of nested if-else, which is easy. But now you need to make sure, does it handle categorical variables? How should it handle it? How does it handle NA variables? There are a lot of little edge cases that needs to happen. Also, the parsing can be dreadfully slow. So I recently improved the Ranger one. I want to say like 1,000 times faster, but it also took like a minute per tree to parse it in a random forest. So there's also like, now you can actually use it, but it takes minutes. But I need to be run faster, but it is a substantial amount of effort for some types of models. Other ones easy, like random forest. Oh, write them from scratch in like 5 minutes, because it actually isn't that hard. Another question. can you extract the raw SQL in a format similar to dplyr show query? What this SQL? So let's actually see. Show query. That's not it. Properly. And if not, that would be easy for me to add. Yes, question in the back.
Is there any useful like visualizations that could come out of this? Or are there like limits that are not possible by stating these models in these terms?
So the question is if there's any useful visualization that come out of this. So maybe it's not something I've thought about a lot. All of what we're doing here is mimic what happens in the real model. So we're technically not writing. We're not actually pulling out their code. We're just analyzing, knowing how a tree works, and then generating whatever. So, we are doing something very similar to what a lot of the visualization software is doing. So if you want to plot a decision tree, for example, they're doing the same thing I'm doing, but they pull out all the numbers and path to figure out how to draw it, and I'm doing it to figure out how to generate code. Another thing I didn't show is you can technically also generate non-R or Python, like you can also generate JavaScript, or if you really want to, you can generate Java or like C, because with a little bit of overhead, it isn't implemented, but it's very easy to do. So I was able to, in a different variation of these slides, I created a JavaScript function that also runs prediction. So basically, you can make a website where there's a predict, like an input drop down or whatever for each like variable, and you put everything in a drop down, or you change the value in a value box, and the predictions happen like that. So now we are essentially having predictions on other people's computers at need be. It's a terrible idea if you care about safety, because you're essentially uploading your predictions for other people to see, but they just see it. But if you do something simple, like if you're like Taverna and you want to expose your guesstimate, you should use something like this to automate this process. All right, any other questions? If not, question over here.
I'm just throwing it out there because I
Yes.
haven't figured out a good way to do row-based simulations with Spark tables,
Yes.
Spark data frames. I didn't know if maybe this could be used somehow to do that.
So the question is, this person has issues with looking at row-based simulations in Spark. So everything Orbital is doing right now is static calculations. So there's no randomness inserted in it, but you might be able to do you should maybe do it in a roundabout way of, depending on what you mean by row-based simulation, but the prediction is in a way a data generating process. So you can at one stage sample from some distribution of your users and then run that into your orbital model to generate something. But the randomness itself, I don't know about, especially in Spark, who's a little interesting. All right. So I think that's everything we have. Javier, do we need to do anything at the end?
One more Slido question.
Which one?
I mean, you don't have to.
Oh, it does what?
Oh.
Is that the one?
The show query.
Oh yeah, so I tried that and I don't think it worked.
Okay.
But it should. Like definitely should work. And I might need to write a function for it.
That was my question.
Yeah. It
Yeah, it's just show query is so helpful because I can immediately copy paste it
yeah.
and put it into SQL, like put it into Snowflake or put it into
Yeah.
Databricks or whatever, and it works.
There are ways of doing something like that. If anything, it's in is it this one? No. With this one. Maybe there are ways of doing it, but I might need to manually pipe it up because part of what makes Orbital nice is it has an easy user phase, we think. So we are abstracting away some of these things about making sure the name tolling is done directly in the dplyr things, which also means that this show query might not work directly, but I could make the method work on Orbital for next release. But that's a thing we could make happen. All right. If not, we will. Thank you.
Thank you.
Oh, no.